Good day, grade 11s, and welcome to this new episode of the grade 11 Geography Caps series. And once again, thank you for tuning in. I hope you will get all the help you were looking for. Now, as you can see from the presentation in today's video, we will be starting a new subtopic, which is global air circulation. Now, this means that we've completely covered the Earth's energy balance. So if you haven't watched those videos, guys, please do. So as I said, in today's video, we'll be starting the global air circulation subtopic, and we will be covering the forces actually in today's video. I think it's important that we first cover the forces or the factors that actually cause movement of winds or movement of air, because we will be talking movement of air throughout this topic, actually throughout the atmosphere topic, and so it's a no-brainer that we first start with the forces. A force, guys, is a push or pull, right? So in other words, these are what are responsible for the movement of air, okay, or for the existence of wind, why we have wind. And we'll be talking a lot about air, and we'll be talking about air throughout all this topic. And so it really makes sense that we begin with the forces that are involved here, as well as the relationships between air temperature, air pressure, and wind. I think I did cover this in the previous video. Please check that out. But I'm also going to emphasize that today because I really need you guys to understand how air moves and why it moves, and how does the kinetic energy of air, meaning which the temperature of air, how is it associated with air pressure, as well as how do we get wind, okay? And then in the next video we cover the rest of the global air circulation. Without wasting any time, guys, let's get into it. Right. As I said, guys, we did talk about temperature of air as well as the pressure or pressure differences, which lead to the existence of wind, right? Remember, wind, guys, we said it is moving air. So how does this happen? So let's say we have different weathers on either side of these two, okay? So let's just call this A on the left-hand side and call this B on the right-hand side. So let's say due to the atmospheric condition on that particular day, or due to the weather on that particular day, area A receives intense heat or intense heating, and it receives this from the sun. The sun heats up the surface, right? And the surface gets warm, right? It warms up, warms up, warms up. And then the surface transfers this heat to the air that is directly above it, okay? Right? Transfers this to the air right close to it. And now this air is warm, right? It takes that heat energy and converts it into kinetic energy and gets excited, right? So you have warm air now. Now it is warm air. And warm air, what are the characteristics of warm air? So warm air, first of all, yes, has a lot of energy, and it is light or it is less dense. And because it is light and less dense, it rises up. Okay, I did make an example there, guys, in the previous video of a bucket and a Coca-Cola can. So as I said, guys, if you do not understand this, please go check out the previous video there. Okay, so now you have this warm air and it rises up. It's going to rise up, right? So it rises up, and we called that convection. Okay, the rising up of warm air, or the transfer of heat vertically to higher altitudes. Okay, so this air is moving up, it's rising, it's rising, it's rising, it moves up and up and up because it is less dense, it is light, and we called that convection. So when we talk about convection, that's what we are talking about, the vertical movement of air to higher altitudes. And then we ask ourselves, how much force is this warm air applying on the surface? How much force is it putting on the surface? It is rising up. It is light, guys. It is rising up on top of that. And so how much force is it placing on the surface or exerting on the surface? It's very little force, right? And so because it is putting very little force, it is hence exerting little pressure. Okay, we said that force and pressure are directly proportional. Okay, when the other one is high, the other one will be high too. So because it applies very little force, it therefore applies very little pressure. And so we said that it leaves an area of low pressure on the ground. An area of low pressure on the ground. Okay, that's how we create an area of low pressure on the ground. So that's why we say that warm air is always associated with low pressure, but you have to understand why warm air is associated with low pressure. Why is that? So you have to be able to explain that. Okay. So now an area of low pressure is created because warm air is light, it is less dense, and hence it rises up, exerting very little force on the ground and hence applying a low pressure or leaving or creating an area of low pressure on the ground. Okay, so that is important to note there. So that is the relationship between now temperature and pressure, right? This is warm air, okay? So the temperature is high, right? Okay, high temperature. And as you can see, guys, eventually this warm air rises up and hence little pressure or little force on the ground, right? Creating an area of low pressure. So that is the relationship between temperature and air pressure. That is warm air. Now let's look at cold air. Okay, what if the temperature is low, guys, due to weather conditions? Okay, so now let's say we have a low temperature, right? So if we have a low temperature, that means we have cold air. Okay, sorry about that. So low temperature. Now, what are the characteristics of cold air? First of all, cold air has low energy, does not have the high energy that the warm air has. Low temperature, low energy, guys. Temperature is simply the average kinetic energy of particles. Okay, so when you talk about temperature, you're actually talking about energy, okay, the measure of energy of your particles. Okay, so low temperature, low energy, simple as that. And cold air, we said that it is heavy and dense, right? I even made an example, guys, of a taxi and leaves. Yeah, I'm really emphasizing this because this is one of the foundational principles of climatology. So all the way to grade 12, these principles are going to be very important. Okay. So now we have cold air. We said that it is heavy, right? It is heavy, it is dense. So cold air has particles that are very close together, compact particles. Something that is dense, guys, is something that is made up of things or particles that are very close together, like there's no space. Okay, it makes it dense, it makes it heavy, and yeah, as I said, very little space in between the particles. Okay, they have no energy, so you cannot expect cold air to rise up. So this is my cold air, and cold air is heavy, it's dense, it tends to stay on the ground, it sits on the ground, applies pressure on the ground. Okay, puts a lot of force on the ground. So it applies a lot of force on the ground. It is heavy, guys. So if it applies a lot of force on the ground, what does that imply? Okay, so if it applies a lot of force on the ground, then that means that it applies a lot of pressure on the ground. And so it creates an area of high pressure on the ground. Okay, see an area of high pressure there on the ground. And that's why we always say that cold air is associated with high pressure because it applies a lot of force on the ground and hence a lot of pressure on the ground. High force, high pressure. Okay, right. So now we have a high pressure on B and a low pressure at A. And so what happens now? We have pressure differences. And whenever you have pressure differences, that's when we start to talk about pressure gradient force. Whenever there's a difference in pressure, guys, this force will start acting upon air and will push air from an area of high pressure towards an area of low pressure. So that is the pressure gradient force. It is a force that exists when you have pressure differences, and that pushes air from an area of high pressure to an area of low pressure. Okay, and therefore causing wind. It causes wind. Okay, so this will result in wind because now you're going to have this cold air at B moving towards A, and it is pushed by the pressure gradient force, right? It pushes the air from B to A. Okay, so that is very important to note there. The relationship between temperature and pressure and the resulting wind, okay, due to the pressure gradient force. I'm going to be using the acronym PGF throughout. So yeah, when I'm writing PGF, please don't be confused. What I mean there is pressure gradient force. Okay, so this is the force that exists when you have pressure differences and that causes air to move. So now this cold air will move all the way towards A, like that. Okay. Right. Before I move on, guys, I want to discuss why why warm air rises up. Why do we have warm air rise up? What causes warm air to rise up? Well, we've already discussed one of that. We said that warm air rises up because of intense heating. Okay, where we said the sun heats up the surface and the surface heats up the air, and the air gains kinetic energy and expands, rises up, and is less dense, and therefore creates an area of low pressure. Okay, that's how we create an area of low pressure. Number one, that's one way to create an area of low pressure, through intense heating. Number two is upliftment by cold air. Okay, so what do we mean there? This is gonna be crucial in the next video. This is what we mean. We mean that when you have cold air, okay, approaching warm air, right? And it's actually going to be important in grade 12 as well, actually. So you have cold air on this side and warm air. They are moving towards each other, right? So what happens? So when you have cold air and warm air moving towards each other, because cold air is heavy, okay, we said cold air is heavy, right? So cold air, what it tends to do is that it tends to wedge underneath. We use the term, it wedges underneath, or we say it undercuts the warm air. That means that it basically moves just below the warm air, and hence by doing that, it pushes the warm air to rise up. Okay, so it's sort of like a shovel. So when you are digging in the ground, you basically take that soil and basically just, and you are going underneath, right? So the shovel goes underneath and the soil goes upwards, like that. Okay, so it's sort of something like that, I guess. The cold air wedges underneath, right? It under wedges. It moves underneath the warm air, and hence forcing the warm air to rise up. So the warm air now is pushed upwards. So it is pushed upwards by upliftment. It is lifted upwards. Okay, the reason why it rises upwards is because it is pushed by the cold air. And then when it rises up, it's therefore going to leave an area of low pressure. It leaves an area of low pressure because it rises up, it does not apply a lot of force on the ground. Okay, so that's two ways we create an area of low pressure. It's number one, intense heating, and number two, the result of the interaction between cold air and warm air. Okay, the upliftment of warm air by cold air. Okay, it is pushed upwards by cold air. Okay, so I need you to note those. Okay, that's how we create an area of low pressure. Right, so back to this. This is what we have now. Now I have these two cells right over here. You guys must have covered these, grade 10, right? So what type of pressure is this? Okay, what type of pressure is this? You're going to see these in your synoptic weather maps. So what do we call these guys? This is a high pressure cell, guys. And the reason why is because, well, the pressure increases towards the center. If it increases towards the center, you can see it went from 980 hectopascals. Okay, let's not forget that, hectopascals. Or they can use millibars actually. Okay, MB. Yeah, 1 hectopascal is equal to 1 millibar. So the pressure is increasing, and so this means that the highest pressure is right over there. Okay, so this is a high pressure cell. So yeah, you should expect these type of questions even in the exams. And on this side, we can tell that we went from 1000 to 980 to 990, and so this is your low pressure cell. Okay, this is a low pressure cell. Another thing that I want to also mention is the difference between consecutive isobars or consecutive isobaric values. So the difference between 1000 and 980, what is the difference there? And I think this should actually be, should have been 990 here. I'm sorry about that, guys. So this should have been 990 over here, actually. And then 980 over here. Yeah, I'm sorry about that. Okay, so from 1000 to 990 to 980. So the difference between consecutive isobars, we call that the isobaric interval. So the difference is how many hectopascals? It is 10, right? So it's 10 hectopascals. So yeah, 1000 minus 990, or you can say 990 minus 980. That's how you get the difference. So that's what we call an isobaric interval. And so now you have an area of high pressure on the right hand side, on the left hand side, I mean, and an area of low pressure on the right hand side. And so what happens? There's a pressure difference, right? And now the pressure gradient force will act upon air. It will now cause the air on the left hand side to move towards the air on the right hand side. Okay, from an area of high pressure to an area of low pressure. Okay, so that's exactly what happens there. And the pressure gradient force is always perpendicular to isobars. Okay, it's always going to move perpendicular to isobars. I will demonstrate this as we move on, but this is important to note that the pressure gradient force is always perpendicular to isobars. So that's what we mean there, guys. The pressure gradient force moves air from an area of high pressure to an area of low pressure. All right. Now let's move on and let's talk about the pressure gradient. What is the pressure gradient and how does it affect wind speed? Because it has a relationship with wind speed. And so it's important to note that that could even be asked in your map work and your synoptic weather map. So what do we mean when we talk about pressure gradient? What is pressure gradient? Pressure gradient is how fast the atmospheric pressure changes with distance, with horizontal distance. How fast, how quickly is it changing? Is it changing too much? Is it changing really fast with distance? Or is it changing very slowly with distance? Right? So that is what pressure gradient is, guys. It is the rate of change of pressure with distance, with horizontal distance. That is pressure gradient. How fast is it changing? Is it changing too much or is it changing very little? All right. So we say that you have a steep pressure gradient when it is changing too much, like very fast, changes quickly over a given distance or over a short distance, right? And we say that it is a gentle pressure gradient when it changes slowly. Okay, when it changes fast, we say that pressure gradient is steep. It is a steep pressure gradient. And how do you see that on the map? You identify that by looking at the proximity of individual isobars. How close are they? If they are very close, the isobars on the synoptic weather map, if they are very close, then you have a steep pressure gradient there, right? As you can see, guys, right over here, you have isobars. These are isobars, right? All of these are isobars, and isobars, guys, are lines that join areas of equal pressure. As you can see over here, guys, let's say this distance from here, let's say this is X and this is Y. Let's say the distance from X to Y, let's say it is 200 meters. Okay, just an example, guys. So let's say it is 200 meters, right? And in this 200 meters, we went from 1,000 hectopascals all the way to 974 hectopascals. Okay, it is changing too much. Over these 200 meters, we've changed very quickly from 1,000 to 974, right? And so we say that this is a steep pressure gradient. The isobars are very close together, and hence the pressure changes a lot. It changes quickly, it changes too much. Okay, that's a lot of change over this relatively short distance of 200 meters. Okay, And so when you have a steep pressure gradient, when you have isobars very close like this, when you have a steep pressure gradient identified by close isobars, of course, this has an effect on your wind speed. Your wind speed becomes high. Okay, this results in very strong winds, right? So when you have a steep pressure gradient, that means over there you have very aggressive weather. You have strong winds. A steep pressure gradient causes strong winds, guys. Okay? Steep pressure gradient is associated with strong winds. Okay? So this means that that pressure gradient force will be very high. Okay? It will apply a very big force on the air, and so it moves. So the air will move, of course, to the right. Okay? And moving perpendicular, as we said, guys, it moves perpendicular to the isobars. Okay, so that's the pressure gradient force. So right over here we have strong winds. By just looking at the close isobars, I can already tell that I have a steep pressure gradient, and therefore I have strong winds. Steep pressure gradient is associated with strong winds. Very important to note. Okay, now let's move on then. What about a gentle pressure gradient? A gentle pressure gradient, as you can see, as I said, guys, it means that the pressure changes slowly. Okay, this is the same distance, guys, from x to y. Okay, again, this is x, and that is y, and this is 200 meters, same distance as the one at the top. But over here, you can clearly see that the pressure does not change quickly. Over these 200 meters, we went from 1,000 to 994. Right? So that is the pressure changing slowly, right? So the isobars are far apart. And that's how you identify a gentle pressure gradient, by far apart isobars. This means that the pressure gradient is gentle. Pressure changes slowly over a given distance. Okay? That's how we identify gentle pressure gradient, with far apart isobars. And a gentle pressure gradient, it causes weak winds. It causes weak winds. Okay, so I'm expecting a calm weather at this region. Another thing that I think we have to mention here is that with a steep pressure gradient, warm air, if you have warm air right over here, the warm air will rise up violently. It will rise up very rapidly, like very fast. Rises up very much, like very fast. Okay, so we see rapid rising air. Okay, it rises very quickly because the pressure gradient is strong. And so if it rises up very quickly, remember, warm air, especially if it is moist, it is going to cause clouds. Okay, and because there's a lot of air that is rising up very quickly, it tends to build those tall cumulonimbus clouds, guys. It builds the tall cumulonimbus clouds. The CB is for cumulonimbus clouds. Okay, so wherever you have a steep pressure gradient and there's warm moist air, the warm moist air will rise up very fast, and hence will build these huge cumulonimbus clouds, these tall cumulonimbus clouds, because it rises up very fast. There's a lot of air rising up, and so there's a lot of air condensing, and so there's a lot of water particles that stack upon each other. Okay, remember, clouds are made up of water particles. And so where you have a steep pressure gradient, we're expecting strong winds. We're also expecting cumulonimbus clouds if you have warm, moist air and the right conditions there. And when you have a gentle pressure gradient, we're expecting weak winds because the pressure gradient force pushes slowly, if you can put it that way. So you have weak winds, and if you have rising air here, so the rising air will rise up slowly. So it rises up slowly, rises up slowly, rises up slowly, and so it cannot build tall clouds. By rising up slowly, that means that it's a relatively small amount of air that will build that will condense into clouds, and so usually you're going to get like your nimbostratus clouds or all your other relatively shorter clouds than your cumulonimbus clouds. Okay, so this is important to note, the relationship between pressure gradient and wind speed. right? I've also added cloud type as well. Okay. So what does this look like on the synoptic weather map? I got this from Weather Essay, synoptic weather charts. You can type this in your computer, or in your phone, you will get this. So this is a synoptic weather map, and you can clearly see, guys, that you have areas of low pressure. For an example, right over here, there's an area of low pressure over there, and you have an area of high pressure in some areas, like over here. Okay, and so if you observe this carefully, let's say I'm just going to call this A, and I'm going to call this B right over here, which between A and B illustrates a steep pressure gradient. It is B, right? So B illustrates a steep pressure gradient because you have close isobars. Okay, there's close isobars, guys. They are very close to each other. Yes, isobars never touch, but when they are close to each other, then that means that it is a steep pressure gradient. And so what about the wind speed right over here? We're expecting strong winds, guys. If we had a weather station here, that would prove that. It would support that. And so by just looking at the proximity of isobars to each other, I can already tell that there's a steep pressure gradient, and hence there's strong winds here. And then at A, that is a gentle pressure gradient. A gentle pressure gradient. Okay. Because, well, the isobars are far apart. Okay, as you can see, guys, right? And again, the isobaric interval like goes from 1024 to 1028. That's 1028. So that's 4 hectopascals isobaric interval there. The difference between consecutive isobaric values. So because the isobars are far apart, this illustrates a gentle pressure gradient, and hence weak winds. The wind speed here must be low. It's a weak pressure gradient force there. Okay, so yeah, all right. Hope you understood that, guys. Let's move on then to another force. So that is a pressure gradient force. It moves air from an area of high pressure to an area of low pressure. It's always perpendicular to isobars. And so that is our first force done, the pressure gradient force. And now we have another force. This force, we call it the Coriolis force. So the Coriolis force is a force that is caused by the Earth's rotation. Okay, remember the Earth rotates. So we're saying that this force, that is caused by the Earth's rotation, it changes or deflects the wind's original direction. So to deflect, guys, I don't know if you guys watch soccer, but in soccer we use the word deflection a lot. So if let's say I have a player right over here, okay, and let's say I have a keeper right over here, and I'm kicking this ball. So this is the ball that I'm going to be kicking, right? So I kick this ball in this direction, okay, and then it hits this guy's leg, right? It was going this direction, so it was going to go this direction. It was going to go like that, right? But because it hit this guy's direction, it's actually going to change direction and move that way. So it deflected. Okay, I kicked it. It was going in this direction, but it now is going to change because there was a force. This guy's leg changed the direction of this soccer ball. So that's what we mean by that is deflection. That is changing the initial direction of something, of whatever. Okay. So in this case, this guy's leg, or the force that this guy's leg produced or exerted on this ball, changed the direction of this ball. Okay, it deflected the direction of this. So by deflected, by deflection, we mean that it changed direction. Okay. Right. So that's what we mean there. If air was supposed to move straight like that, it will no longer move like that. It's actually going to be deflected. Okay, maybe that direction. Okay, so that is the effect of Coriolis force. Okay, the only reason air would move is if you have pressure differences. If there's a high pressure here and there's a low pressure there. Okay, it was supposed to move from a high pressure to a low pressure straight, but because of the Coriolis force, it then is deflected. It changes its direction. It was supposed to move this way, but now it moves that way. So that is that is what Coriolis force does. It is a force that changes or deflects the wind's original direction. In the northern half of the Earth, right, the Coriolis force deflects winds to the right of their original path. To the right of their original path. In the northern hemisphere, if air was supposed to move from, let's say, I don't know, A to B, okay, so it was supposed to move this way, right? So let's say A, of course, is in high pressure there, B, there's a low pressure, and it's the pressure gradient force that is, of course, causing air to move, pushing the air to move. It was supposed to move like this if there was no Coriolis force. But because there's Coriolis force, it is going to move to its right. To its right. So to its right, that means it's going to move this way. Okay? Instead of moving straight, it is deflected by the Coriolis force. If it was going to move, I don't know, let's say from here to, let's say to there. Okay? It's going to move in what direction? What is to the right of this? Okay, imagine you are this air, right, moving like this. What is your right, guys? Okay, what is your right? Your right is this side. Okay, the right of this air. Okay, imagine you are that wind. Your right will be this side, right? Your head is pointed this side, is moving. It was supposed to move this side, and so your right will be like that. Okay, so I need us to really understand the point of reference here. Okay, if the air was supposed to move from here, let's say to there, due to Coriolis force, it's going to move to its right. And so where is it going to move now? It's going to be deflected and move that way. Okay, it moves that way. That is its right. That is its right. That is its right. Okay, so that is the northern hemisphere. Air is deflected to its right. Right, in the northern hemisphere. In the northern hemisphere. Okay, let's note these guys. And then in the southern hemisphere, it's a different story. In the southern hemisphere, where we reside, the Coriolis force deflects wind to the left of their original path. So winds are deflected to the left, to their left in the southern hemisphere. So if air was supposed to move from, let's say, from A to B, okay, it was supposed to move this way, like that, right? From A to B, like that. But because of the Coriolis force, it is deflected to its left. To its left. Okay? That means that, okay, this is in the southern hemisphere. It is deflected to its left. That's how you identify where this wind is located. So what about if it was supposed to move from here to there? Okay, it was supposed to move going down like that. Again, guys, air doesn't just move, okay? So this, it will only move if you had an area of high pressure, then area of low pressure, right? Pressure gradient force moves it. And instead of moving from there to here, it's actually going to move to its left. Where is its left, guys? Where is this? Where is its left? Its left, okay, imagine you are this air. So your left would be, that is your left, okay? So I need us to note these, okay? Very important to note, right? Moving from here to there, okay, you're supposed to move this direction, in this direction, but due to Coriolis force, you're going to move, it's going to move to its left. This is its left, okay? All right, just imagine you are that wind or you are that air, guys, okay? So that is the Coriolis force, guys. So again, here in the northern hemisphere, which is the northern part of the Earth. So again, if we are going to move from A to B, right? I'm supposed to move like that, but due to Coriolis force, this wind or this air is going to move that side to its right. Remember, this is the northern hemisphere. And if this is the and if I have air that was supposed to move from A here to B, okay, just making an example here, guys. Okay, if it was going to move from there to there, it's actually not going to move in that direction. It's going to be deflected to its left, so it's going to move that way. Okay, so it's deflected to its left in the southern hemisphere and deflected to its right in the northern hemisphere. All right, so that is Coriolis force. When it comes to the Coriolis force is actually weakest at the equator and is strongest at the poles. Okay, that has something to do with the Earth's rotational speed or the differences in rotational speed. So the equator's rotational speed is not the same as the pole's rotational speed. So the Coriolis force, we're saying that it is weakest at the equator. So in other words, there's no Coriolis force at the equator. So air there is not deflected actually. So particularly between 0 and 5 degrees north or south of the equator. 0 and 5 degrees, there's no Coriolis force, guys. Coriolis force starts above 5 degrees. Okay, from 6 degrees, 7 degrees, that's where you're going to get Coriolis force. But between 0 and 5, like at 3 degrees, no Coriolis force at all. So there's no deflection there. And it is strongest at the poles. Okay, so we see a strong deflection at the poles. Okay, so meaning which its strength, the Coriolis force's strength increases from 5 degrees all the way to 90 degrees. It becomes strong and strong and stronger as it approaches 90. And in the northern hemisphere as well, becomes strong and strong and stronger as it approaches 90. Okay, right. So that is the Coriolis force, and I think that's all you need to know there. And now we're going to talk about the relationship between the Coriolis force and the pressure gradient force. Okay, these two forces, what kind of relationship do they have and what kind of effect do they have on wind? Okay, so as a result, what happens? We talk about this term, which is the geostrophic flow. Geostrophic flow is simply, guys, an air movement, okay, or a wind direction, okay, that results when the pressure gradient force and the Coriolis force are in equilibrium. Okay, equilibrium means in balance. They have balanced each other. Okay, equal. Okay, and this air movement usually occurs at higher atmosphere, like upper atmosphere, like above 600 meters, where there is less friction. So as you go up, the friction becomes lesser and lesser, and that's we see this behavior there. Okay, at upper atmosphere. So it's basically an air movement that is caused by the balance of PGF and CF. Okay, those two forces. All right, so that is geostrophic flow. Okay, geostrophic flow leads to geostrophic wind. We'll talk about geostrophic wind. Stay with me here. We said that the PGF always moves perpendicular to isobars. It's always going to be perpendicular to isobars, the pressure gradient force. That's how you identify it. Even if they don't tell you, if they have isobars and they have an arrow, and that arrow is perpendicular to those isobars, that is pressure gradient force. Okay, that's how we identify it. It's always perpendicular to isobars. And then the Coriolis force, on the other hand, is perpendicular to the pressure gradient force. Okay, and the pressure gradient force is perpendicular to isobars. Coriolis force, on the other hand, is perpendicular to the pressure gradient force. Okay, all right. So these two then interact. Okay, they interact, and as a result, the wind intersects the isobars diagonally. Let's demonstrate this, guys. Okay, let's demonstrate this here. Okay, they like to have these diagrams. Okay, I don't know if you guys have noticed, but most probably in your exam or in your test, you will have this. On the left hand side, I have isobaric values. So we went from 1,000 hectopascals all the way to 950 hectopascals. So the highest pressure is at the bottom and the lowest pressure is at the top. So what do we expect? Is air going to move from B to A or from A to B? Okay, where is it going to move? Air. Is it going to move from B to A or from A to B? It's indeed going to move from A to B. Okay, and it will be caused by the pressure gradient force. And remember, the pressure gradient force is what is perpendicular to isobars. Okay, so it's supposed to move like that. If there was no Coriolis force, it was going to move like that, just straight from A to B, from the highest pressure to the lowest pressure, being pushed by the pressure gradient force. But now, guys, there's Coriolis force. So we know that pressure gradient is supposed to push air from right over there all the way in a straight line perpendicular to isobars. But now, because you have the Coriolis force, we said that is perpendicular. It is perpendicular to the pressure gradient force. Okay, so this is the pressure gradient force, and this is Coriolis force. Okay, it is perpendicular to the pressure gradient force. So that is our Coriolis force, perpendicular to the pressure gradient force. Right? Okay. Now, this is how it starts, guys. Okay, the pressure gradient force, yes, moving in that direction because, well, it pushes air from a high pressure to a low pressure, and it is perpendicular to isobars. But the Coriolis force is perpendicular to the pressure gradient force. Okay, right? Now, as time goes on, okay, so this is how it begins. But now, as time goes on, we find out that the angle between the pressure gradient force and the Coriolis force actually gets bigger and bigger. Okay, so from 90 degrees straight, now it's about, let's say, 120 degrees, right? That is the Coriolis force right over there. Okay, and of course the pressure gradient force is not going to change. It will remain in that same direction. It's the Coriolis force that keeps on widening that angle. Okay, again, pressure gradient force is still going towards B, whereas the Coriolis force is opening that angle between it and the pressure gradient force, as you can see. Right now it's like 160 or let's say 150. Pressure gradient force still straight like that, and the Coriolis force is opening. Okay, I'd say it's about 175 now, the angle, right, between the pressure gradient force and the Coriolis force. And now, as you can see, pressure gradient force is still moving in that direction. Now the Coriolis force is now directly opposite the pressure gradient force. In other words, it is in balance. Okay, this is what we call equilibrium. It's exactly 180 degrees, the angle between these. Right, this is the pressure gradient force at the top and the Coriolis force at the bottom, and this will be constant. Actually, this will remain like this. Okay, the pressure gradient force and the Coriolis force will remain in equilibrium going forward from this point. Okay, remain in equilibrium. So that's the end result there. Okay, these end up in equilibrium or in balance. Okay, so that's what we see, guys, right? And when we try to draw a trajectory or a path of this air or this wind, remember moving air is wind, we see something like that. Okay, guys, I really tried. I really tried, okay? So we see something like that, okay? So this is the wind now. The wind is moving diagonally, okay? It cuts these isobars, okay? The resulting wind cuts these isobars, and eventually, okay, if you take a look at the end result here, eventually it is moving parallel to the isobars, okay? A wind that is parallel to the isobars, we call that the geostrophic wind. So geostrophic wind is simply a wind that, or a theoretical wind that moves parallel to isobars, constantly parallel to isobars. So it's going to carry on in that direction, um, yeah, theoretically forever and ever. Okay, like that. Okay, so so this is because now the pressure gradient force and the Coriolis force are in balance. They are in equilibrium. Okay, so that's what we see here over time, guys. Instead of moving simply from A to B, because of the balance between PGF and CF, it moves the wind diagonally like that and results in geostrophic wind, air that moves, or moving air that moves parallel to the isobars. Yeah, as I said, guys, without the Coriolis force, air would have moved in a straight line from A all the way to B, just like that. But because there's a Coriolis force, as soon as air moves, it gets deflected, right? As the Coriolis force acts perpendicular to the pressure gradient. Okay, so it moves in that direction. If someone is pulling you in this direction and the other one is pulling you in this direction, you are definitely gonna move in that direction. Okay, so so that's why it moves in that direction. Okay, you have those two forces there, and as air moves, the angle between the PGF and CF increases till they are perfectly in equilibrium, like 180 degrees. So this results in a wind that moves parallel to the isobars, and we call that wind geostrophic wind. So instead of just moving, so again here I have two cells. I have this pressure cell, so that is a high pressure cell, and that is a low pressure cell, right? So instead of having air moving straight like that, it's actually going to move in a diagonal manner, something like that, okay? Because of the Coriolis force. I really hope this made sense. I really hope so. I tried my best. I pray that you understood me all the way. In the next video now, we will be covering the major winds, okay? The tropical easterlies, polar easterlies, westerlies will be covering. We'll be talking about the world pressure belts. We'll be talking about the tricellular circulation, Hartley, Ferrel, and polar cells. So we'll cover a lot in the next video. I'm actually going to just combine all of that, and then we'll just be left with MS characteristics as well as winds related to regional and local air movements. Yeah, thank you. Thank you for tuning in, and I'll see you in the next one.